Welcome to this coding problem walkthrough. Today, we'll be tackling an interesting dynamic programming challenge from problem number 309, titled Best Time to Buy and Sell Stock with Cooldown. This problem is a great exercise in optimizing your decision-making process while considering constraints like cooldown periods. Let's dive in. In this problem, we are tasked with maximizing profit through stock transactions given a specific constraint. You are provided an array called prices, where each element represents the stock price on a specific day. The goal is to determine the maximum profit you can achieve by choosing a single day to buy a stock and a different day in the future to sell it. However, there is an important restriction: after you sell a stock, you must observe a cooldown period, meaning you cannot buy stock on the very next day. This cooldown constraint adds complexity to the problem. Additionally, you are allowed to perform multiple transactions, but not simultaneously. In other words, you need to sell your currently held stock before you can proceed with buying another one. The input to this problem is the array prices, which can have a length between 1 and 5,000, and its elements represent stock prices ranging from 0 to 10,000. The output is a single integer representing the maximum profit you can achieve while adhering to these rules. Let's explore an example to better understand the problem. Suppose the input prices are 1, 2, 3, 0, 2. The output, in this case, would be 3. Here's how this result is achieved. On day 1, you buy the stock at a price of 1. On day 2, you sell it at a price of 2, yielding a profit of 1. On day 3, because of the cooldown constraint, you cannot make any transactions. On day 4, you buy the stock again at a price of 0, and finally, on day 5, you sell it at a price of 2, gaining another profit of 2. Adding these profits together, 1 from the first transaction and 2 from the second, gives a total profit of 3. Now consider a simpler example where the input prices consist of just one day, 1. Since there is only one day, no transactions can be made, and the maximum profit is 0. Another example to examine is the input, 1, 2, 3, 4, 5. Here, the prices are strictly increasing, and the output is 4. To achieve this, you would buy on day 1 at a price of 1, sell on day 2 at a price of 2, and take a cooldown on day 3. Then, you buy again on day 4 at a price of 3, sell on day 5 at a price of 5, and the total profit becomes 1 from the first transaction and 3 from the second, resulting in a total of 4. Breaking down the last example further, here's the reasoning. On day 1, you buy at a price of 1, and on day 2, you sell at a price of 2, giving a profit of 1. Due to the cooldown constraint, you refrain from buying or selling on day 3. On day 4, you buy again at a price of 3, and on day 5, you sell at a price of 5, gaining another profit of 2. Adding these profits together, 1 from the first transaction and 3 from the second, results in a total profit of 4. Lastly, let's review the constraints and edge cases. The array prices can have up to 5,000 elements, and each price can be as high as 10,000. For edge cases, when the array has only one day, no transactions are possible, and the profit is 0. Similarly, if prices are strictly decreasing, no profitable transactions can be made, so the output is also 0. On the other hand, if prices are strictly increasing, the best approach is to buy on the first day and sell on the last day, while respecting the cooldown periods. Lastly, if all prices are the same, no profit can be generated, resulting in an output of 0. To solve this problem, we can start by considering a brute force approach. The intuition behind this method is to try all possible combinations of actions, buying, selling, skipping, or taking a cooldown, to determine the maximum profit. Each decision is made for every day in the given price array. For example, on a particular day, you could decide to buy a stock, but only if you don't already own one. Alternatively, if you currently hold a stock, you could sell it. You also have the option to skip the day without making any transaction. Additionally, if you have just sold a stock, you must take a cooldown on the following day. However, this approach becomes highly inefficient as the number of days increases, due to the exponential growth in the number of possible combinations. Specifically, the time complexity is 2 to the power of n, since each day involves two major decisions, whether to make a transaction or not. While this method is simple and intuitive to implement, it quickly exceeds time limits for larger inputs, making it impractical for this problem. Now, to overcome the inefficiency of the brute force method, we can optimize our solution using dynamic programming. The key insight here is to track the state of the system on each day, which allows us to make decisions based on whether we currently hold a stock or not. Importantly, to handle the cooldown period, we define 3 states. First, there is the holding state, which represents the maximum profit possible if you are holding a stock at the end of a given day. Second, the selling state represents the maximum profit if you sell a stock on that day. Finally, the cooldown state captures the maximum profit when you are in a cooldown period. The transitions between these states are defined as follows. If you are holding a stock, you can either continue holding from the previous day or buy a stock today after a cooldown. If you are selling, you sell the stock you were holding from the previous day. For the cooldown state, you either remain in the cooldown or enter it after selling a stock yesterday. These transitions ensure that we account for all valid scenarios while adhering to the cooldown constraint. To implement the dynamic programming solution, we need to define our base cases. On the first day, if you decide to buy a stock, the hold state will be initialized as negative of the stock price since you are spending money. The sell state will be 0 because selling is not possible on the first day, and similarly, the cooldown state will also start at 0 since no transactions have occurred yet. After processing all days, the maximum profit can be found by taking the maximum of the sell and cooldown states on the last day. This is because holding a stock on the final day is suboptimal. You would have a higher profit by selling it earlier. The time complexity of this approach is O(n), as we only iterate through the prices array once, and the space complexity can be reduced to O(1) by reusing variables instead of maintaining full arrays for the states. While this method requires careful handling of transitions, it is both efficient and effective in addressing the cooldown constraint. The dynamic programming approach stands out as the ideal solution for this problem due to its efficiency and clarity. Unlike the brute force method, it avoids redundant calculations by leveraging overlapping subproblems, which reduces the time complexity to O(n). Although the state transitions might seem complex at first, they provide a structured way to handle the cooldown constraint explicitly. This balance between performance and maintainability makes the approach not only optimal but also easier to debug and adapt if needed. By focusing on key states holding, selling, and cooldown, our solution ensures that every decision is made with the maximum profit in mind, making it a robust and elegant way to solve the problem. In this problem, we aim to maximize the profit from stock trading while adhering to specific rules. You can buy one stock at a time, provided you don't already own one. If you sell a stock, you're required to wait for a cooldown period of 1 day before making another transaction. Additionally, you can choose to skip any day without performing any action. The challenge lies in optimizing the sequence of decisions, whether to buy, sell, or skip, so that the profit is maximized under these constraints. To solve this, we use dynamic programming. This approach lets us break the problem into smaller subproblems, where we calculate and store intermediate results to avoid redundant calculations. The key here is to track the maximum profit at every step while ensuring that the rules, like the cooldown period, are respected. To approach this problem with dynamic programming, we define 3 states for each day. The first is hold, I, which represents the maximum profit if we own a stock at the end of day I. Next is sell, I, which is the maximum profit if we sell a stock on day I. Finally, rest, I, captures the maximum profit if we do nothing on that day. Now, we build transitions between these states. For hold, I, the profit comes from either continuing to hold the stock we own from the previous day or buying a stock today, which reduces our profit by the stock's price. For sell, I, we can only sell a stock that we were holding from the previous day, so the profit is the stock's price added to the previous day's hold. For rest, I, we either continue resting or rest after selling a stock the previous day. These transitions allow us to calculate the maximum profit for each state on every day. To begin calculating these states, we need to establish base cases. On the first day, if we buy a stock, hold 0 is initialized to the negative of the stock price, as this represents our net profit. Sell 0 is initialized to 0 since we cannot sell a stock on the first day. Similarly, rest 0 is also 0 because no transactions have occurred. The final result will be the maximum profit on the last day, which can only come from either selling a stock, sell, N1, or resting, rest, N1. Holding a stock on the last day would not maximize our profit since we cannot sell it afterward. Dynamic programming is a perfect fit for this problem because it allows us to handle overlapping subproblems efficiently. Using separate states for holding, selling, and resting ensures that we respect the cooldown restriction and avoid invalid transitions. Additionally, space optimization is possible since each state only depends on the previous day, allowing us to replace arrays with variables for better efficiency. The data structures needed for this algorithm are straightforward. We can use arrays to store the state values for each day, or we can optimize the space further by using variables to store the states for only the last 2 days. The input is a single array, prices, which contains the stock prices for each day. The time complexity of the solution is O(n), because we iterate through the prices array once, and each state transition is computed in constant time. The space complexity can be reduced to O(1) if we use variables instead of arrays. There are a few edge cases to consider. If the prices array is empty, there are no transactions possible, and we return 0. For a single day, the maximum profit is also 0 since we cannot both buy and sell on the same day. If the prices remain constant or strictly decrease throughout, the maximum profit remains 0, as no profitable transactions are available. Let's solidify this understanding with an example. Consider the input prices as 1, 2, 3, 0, 2. On day 1, we buy a stock at 1, so hold becomes -1. On day 2, we sell the stock at 2, making a profit of 1, and enter a cooldown period. On day 3, we rest, keeping the profit at 1. On day 4, we buy a stock again at 0, with hold updated to 1. Finally, on day 5, we sell the stock at 2, resulting in a final profit of 3. This example highlights how dynamic programming helps us navigate the decisions of buying, selling, and resting to maximize profit while respecting the cooldown constraint. By calculating and transitioning through the states for each day, we arrive at the optimal solution efficiently. This Python implementation solves the LeetCode number 309 problem using a dynamic programming approach to maximize profit with the cooldown condition applied. We use 3 arrays, hold, sell, and cooldown to keep track of the maximum profit in 3 distinct states. 1. Hold, I, represents the maximum profit achievable on day I if we are holding a stock. 2. Sell, I, represents the maximum profit achievable on day I if we sell a stock. 3. Cooldown, I, represents the maximum profit achievable on day I during a cooldown, no transactions. The base cases are initialized for day 0. Hold, 0, is prices, 0, because buying a stock costs money, negative profit. Sell, 0, and cooldown, 0, are both 0 since no transactions can happen yet. For each day I from 1 to n1, the recurrence relations are hold, I, equals max, hold, I1, cooldown, I1, prices, I, either continue holding the stock from the previous day or buy a new stock after a cooldown. Sell, I, equals hold, I1, plus prices, I, selling the stock we were holding. Cooldown, I, equals max, cooldown, I1, sell, I1, either continue the cooldown or transition to a cooldown after selling the stock. Finally, the result is the maximum profit achievable on the last day, which will be the maximum value between sell, N1, and cooldown, N1, as holding a stock at the end will not contribute to the profit. This approach ensures optimal performance with a time complexity of O(n) and space complexity of O(n) due to the use of the 3 arrays. For further optimization, the space complexity can be reduced to O(1) by reusing variables instead of maintaining the arrays. This is the Java implementation for the LeetCode problem best time to buy and sell stock with cooldown, problem number 309. The logic mirrors the Python solution, using dynamic programming with 3 arrays, hold, sell, and cooldown to track the maximum profit in different states. Key differences include type declarations, the use of math.max for comparisons, and array initialization in Java. The solution is efficient and directly solves the problem as specified. To solve the problem of maximizing profit with a cooldown period, we use a dynamic programming approach. In this example, we are given stock prices over 5 days, 1, 2, 3, 0, 2. First, we initialize 3 arrays, hold, sell, and cooldown, which will represent the maximum profit for holding a stock, selling a stock, or being in a cooldown state, respectively. On day 0, the only action we can take is to buy the stock, so hold, 0, is initialized to -1, which is the negative of the stock price. Since no selling or cooldown is possible on day 0, both sell 0 and cooldown 0 are set to 0. Moving to day 1, we calculate each state based on the previous day's values. For hold 1, we either continue holding from day 0 or buy a new stock, resulting in a maximum profit of -1. For sell 1, we sell the stock we held on day 0, earning a profit of 1. For cooldown 1, we take the maximum profit from either staying in a cooldown state or selling on the previous day, which remains 0. Now, after updating the DP arrays for day 1, we move to day 2, where the price is 3. For hold 2, we calculate the maximum profit by either continuing to hold from day 1 at -1 or buying a new stock, which remains -1. For sell 2, we sell the stock we held at day 1's price of 3, resulting in a profit of 2. For cooldown 2, we take the maximum of staying in a cooldown state or the profit from selling on day 1, which gives us 1. On day 3, the price drops to 0. Here, hold 3 becomes 1, as it's more beneficial to buy at this low price during the cooldown state. Sell 3 results in -1 since selling at 0 doesn't yield a profit. Finally, cooldown 3 becomes 2, as it's the maximum profit from either staying in cooldown or selling on day 2. At this point, our DP arrays reflect the optimal profits for each state up to day 3. Continuing to day 4, where the price is 2, we update our DP arrays once more. For hold 4, the maximum profit remains 1, either from continuing to hold or buying during the cooldown state. For sell 4, we sell the stock we held at day 3's price of 2, yielding a profit of 3. For cooldown 4, the maximum profit remains 2, either from staying in a cooldown state or selling on day 3. With the DP arrays fully updated, we can determine the maximum profit achievable by taking the maximum value between sell 4 and cooldown 4, which is 3. This represents the optimal profit for this example, ensuring that we correctly account for the cooldown restriction while maximizing gains. In this example, the stock prices are given as 1, 2, 3, 4, 5, which increase steadily each day. Using the same dynamic programming approach, we initialize the states for day 0, hold 0 equals -1, sell 0 equals 0, and cooldown 0 equals 0. As we iterate through each day, the hold state remains -1 since it's never optimal to buy again after the first day. The sell state increases by 1 each day as we sell the stock at progressively higher prices. The cooldown state also increases by 1 each day, reflecting the profit from selling on the previous day. By day 4, the maximum profit is found in sell 4, which is 4, as selling on the last day yields the highest return. In the final example, the prices are given as 5, 4, 3, 2, 1, which decrease steadily each day. Since the prices are always lower on the following day, no profitable transactions can be made. The hold state decreases each day as the cost of holding the stock becomes progressively worse, starting at -5 and ending at -1. The sell and cooldown states remain 0 throughout, as no selling or cooldown actions are taken. The maximum profit in this case is 0, which reflects that it's better to avoid any transactions when the prices are consistently falling. The time complexity of this solution is O(n), where n represents the length of the prices array. This efficiency comes from the fact that the algorithm processes the prices array in a single loop, iterating once from the first day to the last. During each iteration, 3 key operations are performed. First, we calculate the value of hold I, which determines the maximum profit when holding a stock on day I. This operation involves a constant time calculation using the formula max, hold, I1, cooldown, I1, prices, I. Second, we compute sell, I, representing the profit when selling a stock on day I. This is another constant time operation, as it only involves adding prices, I, to hold, I1. Lastly, we calculate cooldown, I, which gives the profit during a cooldown period, using the formula max, cooldown, I1, sell, I1. Since each of these operations is O(1), and they are performed in every iteration, the total time complexity is the product of the number of iterations, n, and the time per iteration, O(1). This simplifies to O(n). The space complexity of this solution is O(n), because we use dynamic programming arrays to store state information for each day. Specifically, 3 arrays are utilized. The first is the hold array, which tracks the maximum profit when holding a stock, requiring O(n) space. The second is the sell array, storing the maximum profit when selling a stock, also consuming O(n) space. Lastly, the cooldown array keeps track of the maximum profit during cooldown periods, again requiring O(n) space. Each of these arrays has a length equal to the number of days, n. Beyond these arrays, a few scalar variables like n and I are used, but they contribute only O(1) to the space complexity. When combining the space usage of the three arrays and the scalars, the total space complexity sums to O(n) plus O(n) plus O(n) plus O(1), which simplifies to O(n). When comparing approaches, we see significant improvements with the dynamic programming solution. A brute force approach would recursively explore all possible sequences of actions, buying, selling, and cooling down. This exhaustive method results in an exponential time complexity of O(2 to the power of n), because the state space grows exponentially as the number of days increases. This makes it impractical for large inputs. On the other hand, the dynamic programming approach optimizes this by storing intermediate results, avoiding redundant calculations. By explicitly tracking three states, hold, sell, and cooldown, the algorithm achieves a far more efficient time complexity of O(n) and space complexity of O(n). Moreover, the space usage can be further reduced to O(1) by recognizing that the state for any day depends only on the previous day's state. By maintaining just the previous values of hold, sell, and cooldown in scalar variables, we eliminate the need for arrays, reducing the space complexity to O(1) while preserving the O(n) time complexity. In terms of best, average, and worst-case scenarios, the algorithm consistently maintains O(n) time and O(n) space complexity. In the best-case scenario, where all prices remain constant, no transactions occur. The algorithm still iterates through the array, resulting in O(n) time and O(n) space. For the average case, where prices fluctuate moderately, some buy and sell transactions occur, but the algorithm processes every element with the same O(n) time and O(n) space complexity. In the worst-case scenario, where prices fluctuate daily, maximizing the number of state transitions, the algorithm remains efficient. It processes each price in constant time per iteration, ensuring O(n) time. Similarly, the space usage remains proportional to n due to the dynamic programming arrays. Mathematically, the time complexity is derived from a single loop over the prices array, where each iteration takes constant time. This leads to O(n) time. For space complexity, the three dynamic programming arrays of length n dominate, resulting in O(n) memory usage. When solving this problem, there are several common mistakes to watch out for. First, overlooking base cases is a frequent pitfall. If the input is an empty list or contains only one price, no transactions can occur, so the profit should default to 0. It's important to handle these edge cases explicitly in your code. Another mistake is double counting states, which happens when the cooldown period is ignored. For instance, selling and then buying back a stock on the same day violates the cooldown rule, leading to invalid profit calculations. Inefficient recursion without memoization is another major issue. Without memoization, your solution will repeatedly calculate the same subproblems, resulting in exponential time complexity. Instead, use a memoization table or approach the problem iteratively with dynamic programming. Incorrect transition logic is yet another common error. For example, mixing up the states for holding versus not holding stock after a cooldown leads to flawed transitions. Lastly, in languages like C++ or Java, you need to be mindful of integer overflow. When dealing with very large prices or profits, ensure you use the appropriate data types to avoid unexpected errors. Now, let's focus on some interview insights to help you tackle this problem effectively in a coding interview. First, a clear understanding of state transitions is crucial. This problem revolves around managing multiple states, like holding stock, not holding stock, and being in a cooldown period. Be sure to articulate these transitions clearly when explaining your approach. Starting with intuition is another great strategy. Begin by describing the brute force approach, as it demonstrates your thought process, and then discuss how you optimized it. This shows a structured problem-solving approach. Additionally, discussing trade-offs can make a strong impression. For instance, explain why you chose dynamic programming over recursion, and talk about the time-space trade-offs involved when optimizing your solution. Finally, never forget to test edge cases during the interview. Inputs like an empty list, single-day prices, or scenarios where no profit can be made are critical to verify the robustness of your solution. When working on this problem, there are several pitfalls to watch out for. First, not accounting for the cooldown period properly is a frequent issue. Remember, after you sell a stock, you must skip the next day before making another purchase. If you overlook this, your state transitions will be invalid, leading to incorrect profit calculations. It's essential to explicitly incorporate the cooldown period into your dynamic programming recurrence relations. Another common mistake involves the initialization of base cases. For instance, failing to define what happens on day -1 or day 0 can cause logical errors. For example, you might assume that buying before day 0 is valid or that you can have negative profit in certain states, which breaks the solution. Additionally, avoid overcomplicating the state space. Some implementations include unnecessary states in the DP table, which only increases time and space complexity without contributing to the solution. Stick to the minimal and essential states, such as holding, not holding, and cooldown. Finally, be cautious about using plain recursion without memoization. This will lead to exponential time complexity, making your solution impractical for larger inputs. Always use memoization or iterative dynamic programming to optimize the solution to linear time complexity. It's also important to thoroughly understand the problem constraints. A common misunderstanding is assuming unlimited transactions or neglecting edge cases, such as an empty prices array or a single-day input. Carefully reading and interpreting the constraints ensures your solution handles all scenarios correctly. Now, from an interview perspective, this problem is an excellent test of dynamic programming skills. It challenges you to model complex rules while optimizing for the best outcome. Pay close attention to state transitions, as they are the heart of the problem. For example, if you're in a holding state, you can either sell the stock or continue holding it. If you're not holding, you can choose to buy or remain idle. Visualize this as a graph where states are nodes and transitions are edges. Additionally, interviewers may ask you to discuss space optimization techniques, such as reducing the space complexity from O(n) to O(1) by using rolling variables. Make sure you can explain how to store only the last 2 days' states to achieve this. Lastly, paying attention to edge cases like empty inputs, single-day inputs, or scenarios where all prices are the same will demonstrate your thoroughness and ability to handle special cases effectively. This problem is part of a family of stock trading problems, and understanding the relationships between them can deepen your grasp of the concepts. For instance, LeetCode 121 is the most straightforward version, allowing only one transaction. LeetCode 122 builds on this by permitting unlimited transactions, but there's no cooldown constraint. Then there's LeetCode 123, which limits you to at most 2 transactions, introducing another layer of complexity. Finally, LeetCode 714 is similar to the cooldown problem but instead imposes a transaction fee that must be accounted for in your calculations. By studying these variations, you can observe how small changes in constraints lead to different approaches and solutions. This broader perspective can help you quickly adapt to new versions of stock trading problems and demonstrate versatility in interviews. Now, let's discuss some alternative approaches to solving this problem. One option is the recursive approach with memoization. While intuitive and helpful for understanding state transitions, it's not the most practical solution for production use, as it can be slower to implement and debug. Additionally, for larger inputs, it risks stack overflow or timeouts. A more efficient method is iterative dynamic programming, which is the preferred approach. This allows you to solve the problem in O(n) time and O(n) space. For further optimization, you can reduce space complexity to O(1) by keeping track of only the last 2 days' states, though this requires careful management of indexing and transitions. Finally, you might consider a greedy approach, but it isn't applicable to this problem due to the cooldown constraint. However, discussing greedy strategies and simpler variations of stock trading problems can showcase your understanding of when and where different techniques are appropriate. Each approach has its trade-offs, so understanding their strengths and weaknesses is key to selecting the best one for a given scenario. Great work! To summarize, we used a dynamic programming approach to solve the best time to buy and sell stock with cooldown problem efficiently. Remember the key concepts we discussed: state transitions and handling constraints like cooldowns. Thanks for watching, and we look forward to seeing you tackle more coding challenges with us. Don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!